Alright, well today we are talking about section 11-4, which is on the volume of prisms and cylinders. Let's get started. We've been talking about area a lot, so now we're switching gears to volume, which volume just measures the space, which is a three-dimensional term, so the space that a figure occupies. So you're looking at the amount of space inside this box here. Right? So it's not just the area around it, it's how much can fit inside it. And we measure that. So imagine this box is measured in inches, and you want to measure that in terms of what are called cubic inches. So imagine just in this front corner here, right? Imagine that we have a little cube in here, right? That was a terribly drawn cube, I just realized. So imagine there's a little cube in here that occupies this bottom left corner, and that cube is 1 inch by 1 inch by 1 inch. That's called a cubic inch. So I'd be looking at how many of those cubes can I fit inside this box, right? Just along the edge here, I'm just looking at how many cubes can I fit inside this box, and that's what we're measuring when we're measuring volume, for the number of cubes that you can fit inside a specific figure. So that's the concept, that's the overall concept. So I can be cubic inches, we can have cubic feet, we can have cubic meters. If no units are given, you would have units cubed, right? Cubic units. Again, that measures space. Okay? There's a concept, it's called Cavalari's principle, excuse me, that says that if two figures have the same height, so that's a key thing, if they have the same height and the same cross-sectional area at every level, then they will have the same volume. I remember when I first heard this, when I was in high school, I had no idea what they were talking about. So this concept, they try to use quarters, but there's an issue with quarters that if you really think about it, doesn't make sense. So I'm not going to bring that up, even though I just did, didn't I? Anyway, we're talking about post-its here. So there's a stack of post-its right here. And that stack of post-its occupies a certain amount of space, right? Each post-it has a specific area. They all have the same area, and they're stacked on top of each other. Well, this is the same stack of post-its, except it's just slanted, right? So, I mean, you could literally take a stack of post-its and just kind of tilt it to one side a little bit, and you'd get this second picture. But we didn't cut any of the post-its, and we haven't changed the size of any post-its, and the stack doesn't get shorter, right? The stack is the same height. It's just slanted. So these two things, because they are both the same height and they have the same cross-sectional area, which basically means the post-its didn't change size, right? They have the same area at every level. Each level is still just a post-it. Then they would have the same volume. So you can shift them back and forth, the leaning tower and a normal tower, if you will. Or even you can have something like this. We have a rectangular prism first, where the height is, all three of these figures have the same height. The area of that base, that shaded part right here, this little shaded part, the area of that is 6. Well, this second prism, same height, also has an area that is 6, right? It's still a rectangle, or a parallelogram there. No, still a rectangle there. It's just slanted, right? Well, then we also have, that's not a rectangle, that is a parallelogram. But the height of that parallelogram is 2, right? Which means we still have an area of 6. And then if you look at the triangle, again, the same height. And to find the area of that triangle, you do base times height divided by 2, so 12 over 2, which again is still 6. So each of those blue shaded spots, or regions, has an area of 6, and they have the same height, which means you can say that all of the volumes, so the volume of 1, is the same as the volume of 2, which is the same as the volume of 3 here. They're all the same, using Cavalari's principle. Okay? So that's the concept. That's kind of a abstract concept. There's not really much calculations to that. Anyway, today we're specifically talking about prisms. So let's get into how to find the volume of a prism. So you may have this memorized from, when you saw this in elementary school. The volume is length times width times height, right? That's true for a rectangular prism like so, but you can't do that same thing for a hexagonal prism or a pentagonal prism because there's more dimensions than just length times width times height, right? Those aren't the only things that are given to you. But the concept is good. So let's say on the rectangular prism that I am multiplying, or that I have this side as my base. And you can call any of them your base on the rectangular prism because all opposite sides are both congruent and parallel, right? Well, so let's say, imagine that's a piece of paper, right, with a specific area. Well, if I have directly next to that another piece of paper that's like just on the inside here, that was really terribly drawn, another piece of paper that's like just on the inside here, okay, let's say it's right here. It will have the same area, right, and in fact, every piece of paper that I have in here will have the same area because it's a rectangular prism, right? They each have the same area. So the question is, how many pieces of paper could I stack up? Well, however long this is, right? However many inches or feet or whatever units that is, that's how many pieces of paper I could fit in, right? I could fit in, like, let's say this is 10 inches, and I could fit in 10 inches of paper. But to find out how many cubic inches that occupies, it would be however many square inches are here times this 10. So I just have the area of my base times the height of my prism, and that will give you the volume, which in this case happens to work out to be length times width times height. But it's the same for hexagonal prisms and pentagonal prisms. If I can find the area of this shaded spot and then just multiply it times the height, that will give me the volume of that prism. Again, the area of this base times the height will give you the volume of that prism. Let's look at an example here. We have a pentagonal prism. I'm assuming that it is regular, so I didn't add that in here, but I'm assuming the base is a regular pentagon. And so to find the area here of the base, because again, volume is the area of the base times the height, right? To find the area of the base, well, that's just 1/2 AP, or 1/2 the apothem times the perimeter. Well, what's the apothem? Oh, times the, I should put this in parentheses, times the height of the prism. The apothem is 5. The perimeter is 8 plus 8 plus 8. Why am I doing this in white? It is 8 plus 8 plus 8 plus 8 plus 8, or 8 times 5, which is 40, right? So my perimeter is 40. Not 46, 40. And the height of my prism, here, the height of my prism is 10, right? It's 10 inches tall, so I get 1/2 times 5 times 40 times 10, which turns out to be, I would not multiply the 1/2 and the 5 first because it's an odd and it gives you a decimal. What I would do is I would multiply potentially like the 1/2, or let's do 40 times 10, which is 400. Then half of 400 is 200, times 5 gives you 1,000. 1,000 what? We're talking about volume, which means it's cubic inches, right? It's 1,000 cubic inches. So you can multiply in any order using the commutative property. Again, if you did 1/2 times 5 first, you still would have gotten the same thing. Just why add a decimal if you don't need to? So that's the concept. Again, that works for any prism. You just find the area of the base, multiply times the height, and you're good to go. It also works for a cylinder. A cylinder has so many of the same properties as prisms, except for the fact that it's not a prism. That's really the only difference. And it's not a prism because, again, its base is not a polygon, it's a circle. So the concept, however, is the same, where we have the area of the base times the height to give us the volume. Well, what is the area of the base of a circle? Of a cylinder? Well, a cylinder has a circular base, right? Which means that the area of that would just be pi r squared, right? The area of this circle is pi r squared. So B here would be pi r squared, and then times h, right? So the volume of a cylinder is just pi r squared times h. If you want to see it as a completely separate formula to memorize, go ahead. If you just want to remember this, where it's the volume is the base times height, and you can figure out the area of the base, that's fine too, but it's the same principle, and that's important. So, let's look at an example. We have an oblique cylinder, which just means that it's slanted, right? An oblique cylinder. Its radius is 6 centimeters, and its altitude is 8 centimeters. So, a common mistake is, let's say I gave you that the slant height here, let's say I told you that this slant height here was like 11 centimeters, right? A common mistake is to use these two dimensions because they're both part of the actual circle. We do not care about slant height. We only care about the altitude or the actual height, okay? So the 11, I didn't give it to you initially because it does not matter, okay? And that's very important to know. So again, same concept here as before. Volume equals the area of the base times the height of the prism or the cylinder, which is just pi r squared times the height, which is pi times, well, the radius is 6, so we have 6 squared times the height, which is 8. So this gives us pi times 36 times 8, and I forgot to do this ahead of time, so I have to figure out what this is on the fly, which means 36 times 8 is 288, so I get 288 pi. That would be cubic centimeters, which again, just to be clear what this means, this cubic centimeters thing, what that means. That means I can fit 288 pi of these tiny little boxes, right? This little box where, or this cube, I should say, that's 1 centimeter by 1 centimeter by 1 centimeter. That's a cubic centimeter. I can fit 288 pi of these into this cylinder, and it would fill it up perfectly. Okay, so that's what we're solving for. I just wanted you to get a visual of that as to exactly what we are solving for. Okay? That's the general concept there. I encourage you to think about a problem like this, and we'll talk about this more in class. But if you have something like this, where it's a, let's say they give you a prism, rectangular prism like so, but on top of that prism lies a pyramid, like so, perfectly drawn, of course. Right? And they ask you to find the volume of that. I'm not going to give you the dimensions of anything, and you also don't know how to find the volume of a pyramid yet, but the concept I want you to think about. What would the strategy be for finding the volume of that figure? This is called a composite figure. Composite figure. Okay, so figure out, that has an E in it, what the concept would be, and we'll talk about a specific one in class with part of a cylinder on top. So anyway, that's all we have for today. So hopefully you learned something new, and yeah, I'll see you guys later, and hope you enjoyed the video. Bye guys.